Hello all. As a continuation of my lecture series in special electrical machines, we are going to now discuss about the linear analysis of motor performance. So in stepper motor, in the past videos, we have discussed about the construction, principle of operation and modes of operation, and also with the torque prediction performances and torque equations. And now we are going to derive the equation for linear analysis of motor performance. So coming to linear analysis, the linear and non-linear analysis of the motor performance with respect to the torque produced by the motor is explained below. Let us consider, let Tm be the motor torque produced by the rotor in Newton meters and J be the inertia of the rotor and load combination in kilogram meter square. And omega be the angular velocity of the rotor and d be the damping coefficient, or it can be called as viscous frictional coefficient, and theta be the step angle in radians and f be the stepping rate in steps, or we call it as pps, and frictional load torque tf is equal to k into theta. Now, according to rotor dynamics, we can write the torque equation as Tm is equal to J d omega by dt plus d omega plus Tf. So, where J is inertia and d is damping coefficient. Now, we know that theta s stepping angle can be written as theta, which is equal to omega t. So, from which we can write omega is equal to theta s by t, which is 1 by t will give you f. So, f into theta s. So, this makes equation 2, where f is equal to 1 by t. So, that is why we have substituted f is equal to 1 by t in equation 2 and obtained f. And now substituting omega is equal to f into theta s in equation 1, then the Tm is equal to j into df theta s by dt plus df theta s plus tf, which makes frictional torque. And so theta s can be considered as constant, therefore Tm is equal to j into theta s, which is inside the differentiation, can be brought it outside and we can write it as df by dt plus d into, similarly for the next term, theta s is brought outside and we can write it as f plus frictional torque tf. So this is the basic equation. And coming to the damping coefficient, now if the damping coefficient is neglected, then we can neglect d, we can consider d is equal to 0 and the equation becomes Tm is equal to j d omega by dt plus tf. And let us make d omega by dt. So the tf on the right hand side is brought to left hand side, which makes minus, and the final omega equation gives Tm minus Tf by j into t plus omega, where omega is integrating constant, and mathematically we know that omega is equal to theta into f, which makes omega 1 is equal to theta 1 into f1. So by substituting this, the final stepping rate f is equal to Tm minus Tf by j theta s into t plus f1. This makes the final equation. So in this equation, we have linear and non-linear acceleration to find out the motor performance. So in this, we have considered the motor dynamics and we have made the first equation like Tm is equal to j d omega by dt plus Tf. So with this equation, we are substituting the angular value step angles, and we are neglecting the damping coefficient and determining the final equation. A similar way we are going to analyze the non-linear analysis also. So these linear analysis of motor performance will be helpful for us in order to know the rate of the motor, at what step it will have what's the torque. Since it has no continuous rotation, since it is step-by-step operation, we are considering rotor dynamics as the base equation in order to determine the stepping rate. So assessment 1. So we have multi-stack variable reluctance stepper motor are widely used to obtain step sizes in the dash degrees is 2 to 15, 45 to 60, 15 to 30 and 25 to 45. So in a multi-stack variable reluctance stepper motor, the stepping angle size is 2 to 15 degrees. What type of feature is combined to make a hybrid stepper motor? So variable reluctance and permanent magnet stepper motor is the type of feature which is combined to make a hybrid stepper motor. Thank you.